Okay, guys, let's go ahead and get started. Today we are going to implement logistic regression on the candidates data set that I posted on Blackboard. So we need to recall a few equations. So first off, so from last time, just a regression. Okay. And we envisioned this as a single neuron neural network. Okay. So for a given input, so we have x1, y1, dot, dot, dot. So we have n data samples. And then for each of these features, we feed into this simple neural network, and then we have our bias here. So we have weight1, weight2, and then our bias. And we look at some linear combination of these values here. And then we output a prediction based off of the sigmoid function. Right? And this prediction for a given input I is going to be a probability. Okay. So for our loss function, we use the cross entropy loss. So loss entropy. And that looks like this. So loss cross entropy for this is y hat I, y I. This is going to be equal to negative of y I times log of y hat sub I plus 1 minus y I times log of 1 minus y hat I. Okay, and y hat is simply the sigmoid function applied to the linear combination. So just recall y hat I is equal to sigmoid of say W transpose times x sub I plus B. Okay, so recall that's what y hat is. Now, for a given batch, so if we're going to use batch gradient descent, which uses all of the features and labels, the total cost will be, for given weights and biases, this will be equal to 1 over capital N times the sum I is equal to 1 capital N of the cross entropy loss on our output y hat by y. So we're summing this negative value here. Okay. And For gradient descent, we need to know the partial derivatives. So for the gradient of this cost function, it's the sum of the partial derivatives. So just recall from last time that partial the cross entropy loss WV partial Wj is equal to sigmoid of W transpose times X I plus B minus Y times X superscript I's J. So for the Jth weight, for a given input X of I, we have that. And then for the bias, it's a simple bias. That's just going to be this quantity here. Right, but that's for a single input I. So for the full gradient, for batch gradient descent, so this is for a single input. Now for the full batch, it's going to be partial cross entropy loss for weights biases for J is equal to the sum. So 1 over capital N, I is equal 1, N. So I'll go ahead and I guess I'll write it out. Sigma W transpose I that plus V minus Y times, I'll do this. This notation here. Put in an X of I right there, so you see that the partial here is that. So this will just be the sum of the partials of I equal 1 to N. Weights, bias, and then I. Like that. So it's just summing up all those partials. And then the same thing here, if I put in X, I right there, then we get cross entropy loss, weights, biases of the full batch is equal to the sum, the weighted sum, for the average of those partials. So I equals 1 and that weights, biases, I. So if we consider each of those points, we can calculate the gradient for each of those points, and we take the sum divided by n, and then we would have the gradient pieces for the cost function, and then we use batch gradient descent to optimize the weights and biases. Okay, so let's go ahead and do that now. Okay, so here we are. Be sure to have your candidates data ready to go. So we're going to say using CSV, data equals to CSV dot read the candidates data. Okay. That's going to read the CSV file into a Julia data frame. Okay. And then we can say, let's just go ahead and look at that. Okay. So we have GMAT scores, GPA, work experience, and whether or not they were admitted to this given college. Okay. So we're going to make our X data GMAT, GPA, and work experience. Oh, we'll just start with GMAT and GPA. So X data is equal to 1 comma 2, so that two-dimensional vector for X and zip data dot GMAT and then data dot GPA. And then our Y data is just the labels. X for X and data dot admitted. Okay. All right, so we have two-dimensional vectors for GMAT and GPA, and then we have their admissions, either a yes or a no, based on the 1 or 0. So now we need to find our sigmoid function. Let's do sigma tab like this. X is equal to 1 divided by 1 plus negative x. So next we need our cross entropy loss for a given input x and y. So cross entropy loss for a given x, y, weights, and bias. And then we're going to return the formula I had on the board. So negative y times log of sigma of w transpose x. So we can, instead of doing this piece by piece, we can just use a vector notation here. Plus b minus 1 minus y times log 1 minus sigma of w transpose times x plus b. Right, if you recall, that's my y hat. That's the output. Okay. And then we can define the cost is equal to, so the total cost, the average cost, something like that. And this is the thing that we want to minimize. So this is going to take in our features, our labels, weights, and biases. And we're going to return, I'll just say n is equal to the length of a feature. And then we're going to return 1 divided by n times the sum of cross entropy loss of features I, labels I, weights, bias, for I equals 1 to n. Okay, so that's just taking the average of the losses. Okay. So next, we need to update our feature, our weights and biases, and we're going to do this with like a full update where we calculate the gradient on each of. So this would be maybe something like function batch gradient descent. And we'll put in our features, our labels, weights, and bias, and then we'll pick an alpha. Okay. So let's just say, so del W is equal to, let's say 0.0 for I equals 1 to the length of W. So we're making a vector of zeros, and then del B is equal to 0.0 for our partial derivative with respect to B. So we're just initializing these to be empty. So N is equal to length of our feature set. And then now we have to just calculate the gradient for each of the points in the feature set and then update our weights and biases. So for I equals 1 to N, we're going to say del W plus equals, so we're just summing the partial for each piece. So it's going to be sigma of W transpose times features I plus E, right? And then minus Y, or no, labels I times features I. So that's the partial derivative with respect to the ith feature, right? It's this difference times the value of the feature. And then we got to do the same thing for B. And it's just going to be this piece here now. Copy that. That's equals there in that for loop. And then we update our weights biases. So weights equals weights minus alpha times del W. Bias is equal to bias minus alpha times del B. Okay, and then we want to return W and B. Okay. So let's make sure that this works. So maybe say something like WB is equal to batch gradient of X data, Y data. Let's initialize this to be 0.0, 0.0 for our weights, 0.0 for our bias, and let's just pick alpha to be like 0.001 or something like that. Just to make sure all the dimensions match up. Okay, so we see that our weight vector was has changed, right, a little bit. So maybe what we can do is just like look at the average cost. So just to make sure that we are going in the descent direction. So say like W is equal to 0.0, 0.0. Bias is equal to 0.0. X data, Y data, WB, so I'm going to print that out. And then So I'm going to say something like that. Copy W here, B here, and then down here I'm going to do trend line. The new cost is average cost with our updated. So let's see what this does. All right, so our new cost is higher. But let's see what happens if we run this again. So what this is telling me is that my step size is probably way too big. So I'm going to make it smaller. It's a little bit better. Maybe make it a little bit smaller. Okay, so it looks like, I just iterate this again. It's getting a little bit smaller. So maybe if it's a little bit bigger. So it looks like my optimal choice of alpha in this case is around that small. And of course I can like automate this with a for loop, but I'm just like playing around with it right now. And it is getting smaller. Okay. So now we can write a new function. So I'm just going to copy some code from linear regression. Okay, so this is going to be train batch gradient descent. So this function is called batch gradient descent. So batch gradient descent features labels. Okay, so this is updating W and B, and this is just printing out how many times you run it. Okay, features, labels, effects. All right, so let's run this. Yeah. And then we can say copy, paste, WB is equal to that. And then we can say W is equal to 0.0, 0.0. Now, your initialization of your weights and your bias, we're not always going to use zeros. We can do this randomly, but let's just see what happens when we do this. So X data, Y data, WB, alpha. We up here when we're playing with it, use this as our alpha or our learning rate. And then let's run this like, I don't know, like 10,000 times. Oh. So average cost. I'll just change this to loss for now, just to make it easier. You want to just like get rid of that stuff for now, but so now just run this again. Let's try this. So we can see that the cost is getting smaller, right? Let me just see what happens when I do this randomly. So random from a normal distribution, two-dimensional vector, 1 per century. So you see that here, it was like a huge number, and it keeps on getting smaller. Let's see what happens here. Let's run this. It's getting smaller. Run this. And So maybe the step length is, so, okay. So now starting with the W and B that we created, let's run this again. See how it's getting smaller and smaller. Maybe if we, it's down to 0.8. So starting from a random case, it's taking some time to train. But it is training. You can see that with the loss. So now, instead of starting from there, I'm going to start with, instead of randomly, I'm going to 0.0, 0.0, and then 0.0, change my alpha. So your initial conditions here seem to be working better in this case. So let's keep on training. It's going. And let's just keep on doing this some more. I want to see this loss get lower. It's getting there. I'm gonna do it a few more times. And again, the step size is so small, it's taking us a little bit to train this, right? Oh, what am I doing? I need to, that was my problem. That's why I wasn't decreasing. WB. So now it's going. So now we're getting, so I'm sorry, I kept on initializing W and B to be 0, 0, when I should have used the new W and B that I had. So now we see that we're below 0.6. Let's keep on going. I want to see it get to about 0.50. Now we will talk about overfitting later in a later lecture, but for now we're just trying to get this thing working on the data that we have. And the step size is so small, you see that it's taking forever, even if we're repeating here. So maybe if I make this like a little bit bigger, like 0.6. Oh, that's too big, we overshot. So it's very sensitive, as you can tell. Oh, but then we're good. We're below, we're below 0.5 at this point. Okay, so this is really our epoch. Like we've run this like a couple million times by now. So let's see how well this W and B work. So what I'm going to do is I'm going to write a function here called predict. It's going to take in an X and a Y and our weights and our biases. So if our Y hat is greater than or equal to 0.5, we predict that the student was accepted. And then here, this is just a ternary operator. If the actual label was 1, print was accepted. If not, then you show that it wasn't accepted. If our Y hat is less than 0.5, we predict not accepted. Okay, so let's just like, because this is such a small data set, we can literally print out all the results. So for I and length X data, we're going to make a prediction, and let's see what this does. So what do we see? We see that this student we predicted to be accepted, but indeed they were accepted. But here we see that there's some problems here. Predict not accepted, but they were accepted, right? Predict not accepted, but they were accepted, right? So, okay, there are errors, but that's okay. Notice that up here, though, we only use the first two entries. Let's see what happens if we use work experience as well. So that'll be like x3. And then here, let's do data dot work experience. So nothing else has changed. So all I did was just change the dimensions of X data. And in my code up here, I never specified that it's two entries other than when I manually did that. All right, so everything should be the same. So let's go down to here and maybe change this to 0.0, comma 0.0, comma 0.0. So a three-dimensional weight vector, 0.0, and then that. So whoa, that shot down pretty quick. You see that 0.43? Let's just go ahead and run it one more time by just putting a W and a B. Now that we have a W and B, let's just do that. All right, so that's pretty good. Look at the loss there. So let's see, and we can just run this again. So we see some changes here. We did it wrong there, but down here we're starting to get it right. So this is good. This is learning for the most part here. So if you wanted to look at this numerically, you could change this predict function here. So instead of printing out this, we could actually look at like, so one else zero. So this is our new predict function. So like, there, so 0, and we can just do mean error plus equals predict say X data. Oh, we can just do this. Mirror predict X data. So if that's X data, I, Y data, I, W, B, minus Y data, I. So if that's a 1, and that's a 1, this is a 0, right? So if we predict a 1 and it is a 1, that's nothing. If this is a 1 and that's a 0, that's a 1. So we can just put on this difference square. And then, of course, like you want to put this in a function divided by. I'm just doing this kind of quickly to show for lecture. So there's the average error. So we're good. We don't miss too many. For the most part, with these weights and biases, we're able to accurately predict whether or not the students have been accepted to the university based off of their GPA, whether their GMAT, their GPA, and their work experience in years. Okay? So realistically, this is a small data set, but realistically what you would want to do is you'd want to take something like 75% of the data as your training data and leave out a quarter or something something close to those types of numbers, and then train on a piece of the data set and then test on the data that you have not seen. So for example, what we could do, there's a few different ways we can do this, but I'll leave that up to you to partition the data into a trained data set and a test data set to test how accurate you are on data that you haven't yet seen. Okay, so that is implementing batch gradient descent to train for logistic regression. Okay, so that'll be it for today. Everyone stay safe, and we will pick back up on more supervised learning next time. All right, see you then.